In this video, we're going to be calculating the enthalpy of the reaction using Hess's law, and we'll talk about what the Hess's law is in a minute. Suppose you have this generic reaction where we have A reacting with B2 and it's making an AB2, and this particular reaction has a delta H of negative 100 kilojoules per mole. So right now, this reaction is actually exothermic because it's releasing the heat. So before we actually go and jump into doing a question that involves in a Hess's law, I want to kind of talk about what would you do, what would happen to the delta H's if you manipulate any of the reactions here, like if you manipulate the coefficients or if you flip them. So the first thing is if you multiply the reaction, or another way of saying if you increase the concentrations. So if you multiply by 2, so when you multiply everything by 2 or double up the concentrations of everything, so we have 2A plus 2B2, and that goes on to make 2AB2, then what really happens to this new delta H? Well, in that case, your delta H also gets doubled. So you're going to have 100 times 2, so it's going to be negative 200 kilojoules per mole. Well, same story. If you have the reacting materials and the products, then you will divide your delta H by 2. So another way of saying, what if I have 1/2 A times 1/2 of B2, and that results in the formation of half AB2, then how would your delta H change? Well, in that case, you got to half your original delta H as well, which is going to be 100 divided by 2, and that's going to be 50 kilojoules per mole. Okay, so that's one thing you want to make sure you know. The second, the other thing is, what if you flip the reaction? If you flip the reaction, what happens to the delta H? When we say flip the reaction, what that really means, my product becomes the reactant. So you starting out with AB2, and then it goes on to make A plus B2. So in that case, your delta H also flips in the signs. All right, so your delta H becomes positive 100 kilojoules per mole. What that really means, this reaction will be now an endothermic reaction. Okay, so make sure you know what to do when you're multiplying the reactants or dividing the reactants or flipping the reaction, what happens to the delta H. Now the Hess's law says if I have two reactions, let's say, I don't have a question down there, but before we actually go do the question, assume I have A plus B, and that goes on to make C, so I'm just going to cross the line right there, plus D. Okay, and then we have some delta H for this one. Let's call that delta H1. And I have another reaction where you have C plus D goes on to make X plus Y. Okay, and if I do go ahead and add these two reactions up, so when I add these two up, your common reactants and products will cancel out, so C and D cancels out, so at the end of the day, your A plus B is going to be making X plus Y. And to calculate the delta H for this final reaction, I would have to add up the delta H1 and delta H2. So another way of saying, if I do this reaction two ways, okay, if I go ahead and do A plus B and make X plus Y straight, my delta H, whatever you're going to get, is going to be the same even if you do this reaction in two steps, where first step will be making C and D, and then in the second step that C and D will be converting to X and Y. So this delta H right here, which is the addition of delta H1 and delta H2, would be the same even if you do this reaction straight. So that's what the Hess's law is. All right, so let's apply that into this question here. So we're given we have to use the enthalpies of these reactions right there, and we have to figure out what the delta H going to be. So this is a typical reaction or typical question that involves the Hess's law, where they give you a reaction, okay, and you have to figure out the delta H, but then they give you a couple of other reactions, could be two or maybe more than two, and you have to use these two reactions to get to the target reaction. So another way of saying, you can manipulate the given reactions however you want and then add those up to get to your target reaction. So if I focus on maybe SO3 in the beginning, like in my target reaction, the SO3 is in the reactant. And let's go back and check where the SO3 is in my given reactions. The SO3 is in the second reaction, but that's in the product. Okay? So to get to the reactants, what do I have to do? Well, first I need to flip it so that it comes to the reactants. And then what else I need to do? This is the only source where the SO3 is coming from, and when you look at the target reaction, there is actually 4 in front of SO3. So since there is 4 in front of SO3, I would have to multiply this by 2 as well. So I got to do two things to it. I got to flip it and multiply by 2. So let's go ahead and write that reaction. What's that going to be? So when I multiply by 2 and flip it, it's going to become 4 SO3 gas, and that's going to go ahead and make 4 SO2 gas plus O2 gas. Okay, and then what's going to happen to the delta H here now? Well, when you flip it, it becomes positive, and since you're multiplying by 2, you got to multiply this by 2. So 197.8 times 2 is going to be the new value for this delta H. So let's see what that comes out to be. 197.8 times 2 is going to be 395.6 kilojoules here. Okay? Alright, so what else do we need to do for the first reaction? The only product we have, like the O2 is kind of common in both of the reactions, like O2 is right there and the O2 is right there, so maybe not focus on that one. But when you look, the other one is the sulfur. Alright, so we'll change the color there. So sulfur is in the products in your target reaction, and when you look at the first reaction, it is already in the products, so we don't really have to flip it. But let's check the coefficients. In the target reaction, the sulfur has 4 as its coefficient. Right now, it doesn't have anything. It's got 1 on it, so that means I need to multiply this reaction by 4. So when I go ahead and multiply that reaction by 4, it becomes 4 SO2 gas, and that's going to break into 4 S solid, and then 4 O2 gas. And then we're not flipping it, all we're really doing is just multiplying by 4, so I'm going to have 296.8 times 4. So your new delta H for that reaction is going to be 296.8 times 4 is 1187.2 kilojoules. Okay, now all I really got to do is just add those two reactions up and see what I get. So when I add these two reactions up, your SO2 is going to be common on both sides, so that cancels out. Okay, and then let's see, it's going to be 4 SO3 gas, and that goes on to make there should have been 2 there. I forgot to multiply this by 2. Sorry about that. And because you were multiplying this second reaction by 2 and flipping it, so I forgot to put 2 there. So it's going to be 4S here solid, and then 4 plus 2 is going to be 6O2 here in the form of gas. Okay, so that gives you your final reaction, because that's what you really have on the top here. Make sure you double check with your target reaction. The sum of those two reactions should give you the target reaction. If you don't get the target reaction, that means you haven't added those or flipped those or anything like that correctly. So you got to go back and make sure you fix this. So now your delta H for this reaction is going to be 395.6 plus 1187.2. So you just add both of those up. So that's going to be 1582.8 kilojoules for this particular reaction. So that's how you're going to be using the Hess's law in finding the delta H of a reaction when you're given two or more other reactions. So you add or subtract those up, manipulate those to get the final reaction. All right, so hopefully this was helpful. If you have any questions, leave the comments in the section.